All right, thank you for the introduction. And yes, we'll be using digital twins today to learn how to prove out your program inside the programming room, leaving your machines to be running full time, therefore, like we said, saving time and avoiding costly mistakes. And in doing so, we're going to be learning a little bit about NC-Simul today. As a background, what an NC-Simul digital twin does is a true G-code validation or certification, meaning the same G-code that's going to be running at the real machine is running inside the digital twin. That way you know there are no discrepancies in behaviors in either direction. And in doing that, we'll do a complete machining simulation where you'll see all the material removal come off the part. You'll see all the axes of the machines moving. And then at the end of the G-code process, we'll do a visual part inspection where we'll compare the original part model to what we just cut with that certified G-code, and you'll be able to tell if it's hitting all of its tolerances and that you've created a good piece before you go ahead and walk out there and run it. And a couple of things that are true as of today, we have no limitations on where that G-code is coming from. So regardless of if you're programming from a CAM system, if you have a collection of CAM systems and those programs are coming in from different areas of the shop, or even if you've manually programmed, doesn't matter. We can read all that for whatever digital twin or real-life machine you're using. And that includes all machine types. So 2-axis to Swiss, 2.5 to full 5-axis, mill-turn, multi-channel, all okay under NC-Simul's roof. And how we do that, we connect the digital and physical worlds in this aspect. So any fixture models, stock parts, design parts, cutting tools, and obviously your NC program, those are all incorporated and can be passed either from the CAM system or again created inside NC-Simul. And they all get put into the digital twin. That way we can run everything ahead of time in here. A couple things to keep in mind. NC-Simul is CAM agnostic, meaning that no matter where, again, the G-code is getting produced from, you keep your process the same, and then you transfer that as well as any of the other of those materials that we just saw from there. So these are some of the examples of the direct interfaces that we have that can transfer all of that automatically, but we can certainly import anything if you aren't using one of these in a Parasolid step STL file as you like it. The other thing is that NC-Simul is machine agnostic, so it doesn't really matter which machine you're using. We're going to be able to build a digital twin for it. And as you can see, this is just a few examples of the ones that we have in use today. But as a rule of thumb, we can generally cover absolutely everything. Now, what I'll quickly kind of gloss over is what we're going to see during the demonstration. And you'll see this theme kind of keep coming back up. We have a 3-step process for the G-code verification. The first step is the G-code validation, and this is going to catch anything that would alarm out your real machine. So those will be the out-of-range motions, the overtravels, undefined codes. Basically, if you walked out and loaded the program and the machine alarmed out, you would know that ahead of time inside NC-Simul. The other thing it does during the validation step is it decomposes all of the G-code ahead of time. So you can get the toolpath wireframes as you see in the picture on the right-hand side to make sure that your program's set up properly, as well as exact machine timing calculations. So without even running the whole simulation, you can know how long the cycle time is, and you'll get a full toolpath preview. The second step is the simulation, and this is everything to do with motion in the machine. So this will catch all of your collisions. You're cutting without coolant, cutting without the spindle on, clipping the fixturing, rapid in material, overcuts on the flute length. All of this is done in step 2, and you'll also see all the movements of the machine in the 3D environment, either in machine or table view. And if you're using a multi-channel machine, as the last point is saying, it's going to show the activity between both of the programs side by side, so you can kind of see where the sync points are called for each of those. And the last thing we'll look at today, the step 3, is the visual part inspection. So this again is comparing the original part model to what we just cut with the G-code. And you'll see it show up in a color bar system depending on if you're hitting your tolerance, if you're gouging the part, if you're leaving materials. And in addition to this, we have some extra tools that will help you out other than visually. We have a gouge material analyzer, we have a surplus material analyzer, and then you can also take measurements off the piece, the part, the stock, any fixturing that you need, as well as being able to slice the piece to get any internal measurements that you need as well. And this is the full process in summary. Today we're going to be focusing on the first 3 bullet points, which I just went through. So the G-code validation, the simulation, and the part inspection. But just to let you know, for a future webinar, or if you need some more info about these specifically, we do offer toolpath and power optimization. And at that level, we can reduce air cutting. We can regulate the feeds in material for both chip thickness and chip flow, so volumetric engagement. And we can also utilize the power of the machine so that we don't overrun the spindle in any like heavy machining locations. So that's an option as well. And the final thing is documentation in NC Player. So documentation would fall under the same category. If you'd like some more information on that, just let us know. But basically, we can produce the setup sheets for the shop floor. And it's kind of nice because anytime NC Simul updates, if you change a tool length coming from your import or anything like that, it's going to automatically change that output for you. And the NC Player is included with the software always. So this is a license-free version of NC Simul that you can spread around on the shop floor if you'd like. It runs on any Windows-based tablet or computer, and it's basically a light program or a light version of the program. That way the machinist can see exactly what the programmer was thinking. They just don't have the capability to edit or add any of the code or the process. It just gives them a really good idea of what the part should look like after each tool runs, for instance. Okay, and just some final takeaways before I jump into the demo portion. And you'll see all of these as we kind of go along. The first point you'll see is the ease of use. So at this point, everybody has gone to the tabs and icons version of the software at the top. NC Simul is the same way. You're going to be used to it if you've used Word or Excel or anything. As of recent, everything is laid out for you. The tabs and icons are up front. There's nothing buried in menus that you have to memorize where everything's gone. You can see exactly what you need to use. The next is the strong 3-step process that we've outlined. So once again, verification of the code or validation of the decomposed code, the simulation where the material removal comes off, and the part inspection at the end. The other thing that NC Simul does is it verifies all macros and subroutines in their entirety. So when we're building the machine digital twin, we're going to download the archive from the real machine, meaning that anytime something is called inside the NC Simul environment, and I will show you exactly what I mean when we get into it, that means it's doing the exact same thing that the real machine is using and mimicking what yours is doing exactly. Yeah. So if you change that for any reason, we can automatically change it inside NC Simul with the archive file. And that way you know it's behaving exactly the same way the real one does. Speed of simulation you'll see in the demo, clarity of 3D, the same thing. And then just the last 2 points, the short learning curve. So right now we're offering training online for NC Simul to get you up to speed. And we have it blocked off into 2-hour sessions. So we'll do 3 days of 2 hours on the main functions of the software to get you kind of comfortable with how NC Simul moves. Then the 4th day, we'll do some projects, real-life projects. So you'll come with us to with one of your CAM projects. We'll go through that during the training as if we're trying to really get the part out to the shop floor so you can get a feel for what your day-to-day life would be like using NC Simul. And then we'll have a 5th follow-up session going over anything that you've come across after you've used it for maybe a week or 2 or so. And we can kind of readdress anything that you need. But basically after that, within 10 to 12 hours of training, you're completely self-dependent and being able to use NC Simul. And the last note here is flexible licensing options. So NCSimul can run on a floating network license, meaning that you can put the license on the server, and then if somebody needs it, you can pull that license, use it on your computer, close the software, it'll release the license back to the network, and that way it can be shared across the shop floor, and you can have a seat of NCSimul on as many computers as you'd like, sharing as many licenses as you decide to have. But yeah, that's it. Let's jump into the actual demo portion now. Okay, so this is the main home screen for NCSimul. As we were talking about, you can see up top, you have your famous ribbons and tabs and with all the icons across the top, all Windows-based. And you also have what's called a working environment across the top bar here. Mine says Part Flip. You're welcome to set this up by company name that you're making products for, by part number, by job number, anything that helps you kind of consolidate your resources. But the idea being anything that you create within inside one of those environments are reusable across anything else that you create in that environment. So say you've imported or created a standardized tool list, you can set that to use on the machine every single time that it loads. You can set it to use it every single time you run that job, however you would like to end up setting it up. You can also do things from this window like start a new project. You can set up some automations for your part creation processes. You could create new working environments if you wanted to add a new customer or something like that. But basically what you're looking at here already is a project that I've created inside this environment. And if I click on it once, I get a quick preview of what's actually inside it. So without even having to go into the project and back out in case I was checking for something in particular, you can see what machine this project is running on, or if it has multiple operations with multiple machines, you'll see the list of any that are used there. Inside the process, you could see how many operations you're running, the name of the program that you're running it on. So it's really useful to be able to see all the resources right at the main screen. When I double click the project, it does start, again, the three-step process that we've been outlining. So to hammer it home, step 1, syntax error check. Anything that's going to alarm out the machine is where you're going to see the error messages down here in the information window. Then step 2 is the simulation, where all the material removal comes off. And then inside here, you're really using 3 main buttons. You'll have your reset button, which puts all the material back on to the rough stock and starts the simulation over. You have the play button, which runs the simulation. And then you have a speed of simulation slider, so you can decide how fast compared to real time you want the actual simulation to run visually. And at the end of that, the comparison tool that we were referencing is right here. We can compare the part model to what we just cut. And we'll get to that in just a second. But first, I'll kind of walk you around the screen so you know exactly what you're looking at as I go through the process. The left-hand side over here is what we call the job tree. And this is set up in the same exact way that the process would be set up on the real shop floor. So you have the operation that you're running, the digital twin machine that it's running on, any setups you have for the process, and inside those setups, which I'll get mounted onto the machine table, you have the fixturing, you have the part model, and you have the rough stock. Then below that, we have the tool magazine and tool library, and basically any tools that are created for material removal will be inside these libraries, and they'll be called inside the digital twin spindle. The initialization just tells NCSimul where in space the program resides, so you can make sure that it's kind of in the right area before you even get going. And then finally, the last area here, or the last item line here, is the G-code. So again, the same post-process one the real machine is running. And upon that step 1 of loading, it also breaks it down by tool sequence. So every time there's a tool change, you'll see a sequence. That way, if I wanted to just simulate a few of the selected operations, I don't have to watch the whole code run each time. If I've already seen 1 through 5 in that case, I can watch 6 through 11. Now down at the bottom is the information window, so we've already seen our process errors there upon loading. When we run the actual simulation, if there's any collisions, you'll see them in the same area except in blue instead of this red. The next button over is a status tab, and this is giving you active information about whatever block is highlighted inside your G-code. So I can kind of move down to wherever I want, pick a particular block, and as I do that, both the machine, if I turn on all the wireframes here, both the machine will move to that location and this status will update. So you can see what tool is running in that instance, where you are in space compared to the active reference or your G54, for instance, your machine position. You can see what your length or cutter comp is. All sorts of information is in here. Then we have an information tab, and this is sort of the same, but it gives you the overall values for the program. So broken down by those same tool sequences, you can see how much time each of those tools is running for, how much of that is rapid versus actually cutting. You'll see your feeds and speeds, mins and maxes, and that's dynamic as well, just as the same as clicking on one of the blocks inside the G-code to kind of figure out where you are. You can click on one of the values inside the table or one of the cells, and if I wanted to see, for instance, where that F max is in the first sequence, just click on that 100, and it brings me right to that point in the program and on the machine. The other nice thing it does right up front with this is it shows you your cycle time just based on the feeds and speeds of the program and without even running the simulation. So that's also unique to us. We don't need to run all the material removal to see how long the process is going to take. We can do it strictly from the G-code, which is separated or a separate process from the simulation. That makes it really, really quick for us. So you can see we decoded all of that to figure out the cycle time in 4 seconds. Just two more things down here before we move on. One is a variables tab. So if you have any looping or conditionally formatted programming, you can just add a variable to the right-hand side to track it. And then as that value is updated throughout the process and it's stored, you can make sure that it's taking the proper one and doing what you would expect it to do or store. And then finally, we can look at a graphing tab down here. And this is just a quick visual representation of the motion of the machine. I can click in here and drag bidirectionally, and I'll move again the machine and the G-code. I can jump tool by tool. I can jump stop by stop. Right now I'm just in feed rate by minute, but if I wanted to add any series of variables, I can just add them in that checklist and switch between them with this button. So just a bunch of visual tools down here. Now the right-hand side is the post-process G-code that we've been looking at, plus any subroutines or macros that are pulled from the real machine. So like I was mentioning in the intro, anytime you see something like that, you'll see a little plus sign here with the NC Simul, and if I expand it, you get the decomposed motion that's happening in the background when something's called in the code. In this case, when the tool changes happen, this is the tool change macro that's coming directly off your real machine. That way, you can get a really good and accurate cycle time estimation, as well as making sure that you're not going to see or get any unforeseen collisions when you're exiting the part. If you move Z, then XY versus XYZ at the same time, you'll know exactly how that's going to look ahead of time inside NC Simul. And then finally is just the main 3D window. You have two ways of viewing it. You have this full machine view where you see everything moving in 5-axis, and then you can switch to table view only, where it locks the piece in the Z direction and just shows the tool coming in and moving around to remove material. And what you're looking at here is your red or your rapid motions, your blue is feeding, and if you have cutter comp active, they'll show the wireframes in green. And these are dynamically connected again to the other two windows in the same way. If I wanted to see what tool was responsible for machining a certain line, I just double click right on it, and it lines up the tool for me to that location, shows me my line of code, and then if I went back to the status, it would show me what's going on that line as well. So that's the quick run around of what we're about to use to certify the code. And I'll jump back to the process errors, and we can start the 3-step process as if we were doing this day to day. So the idea with the job tree that I went through is any of those elements can be created inside NC Simul if you want to import them, if you want to make them directly in the software. But if you have these things sitting somewhere in your CAM system already, there's no need to do the work twice. You just import with one of those direct links that I showed in the CAM agnostic page, and this window will be populated for you. So the idea is if you have that ready, the job tree is populated and you're ready to start the three-step process. So step one in that process is getting rid of everything in this window. So I'm just going to click on the first error message, which is telling me my z-axis is out of range. I'm at position 1 and I can only retract to 0 in z, so I'm out by 1. Basically, whatever mounting point I put this fixturing at, when the program's located there, it pushes me to that point. So I can just go over here to the right-hand side, and if I click this icon, the pencil with the star, it's going to turn this into a quick edit mode. And then I can go right into the G-code, make my change directly from here, change my Z value by 1 inch or more, and it just happens to be 1 versus 0 anyway. And then when it does it, it reruns that syntax error check and makes sure that's a new good value. And that's why it's always good to kind of go top to bottom in your error messages, because you see by changing that 1, we had a bunch of extra movements that were at that height. So it gets rid of a bunch of extra errors, which you would have seen if it moved a bunch of times out of the envelope. And that's all there is to do to step 1, kind of move top to bottom. And when you're done, like this is, you should see this window blank, and this button down here is green, meaning we can move to step 2. Now, step 2 is that simulation. And I'm going to slow it down a little to begin with, as we talked about. So we'll have it real time about 10 times as fast as it would go in real life. And we'll just hit that play button to get going. And this again is that 3D view. So you can be zooming in and out as it's machining. I can be panning back and forth. I can change the speed that it's machining at. I can rotate around, change to the table view. It never needs to stop to refresh. It's always clear. I can shut the toolpaths off. And as you can see, each tool that's coming in is machining in a different color. That way you can guarantee each tool is getting to do work. And I can also pause it at any point if you were curious what tool was machining a certain surface. I just double click right on that surface and it's going to line my tool up and tell me the G-code that was responsible for machining right there. And regardless of where you click, as soon as you hit play again, it's going to pick up where it left off in the code and continue the material removal process. This particular one has a part switch, so it finishes the first side. That's why we have 2 operations here. Flips the part with some commands and then continues machining on the second side. So if I just speed it up a little bit, we should be getting to some points where we're going to start to see some errors. And as we do get some collisions, you'll see the process errors occurring down in the bottom down here. Okay, so as you can see, we have some collisions between the tool and the fixturing. That's why they're showing up in purple, because it's a machine element. If it was just tool in the rough stock directly, you would see it in blue. But because they're like this, anytime that I click on one, it's going to give me a good red circle right around the part, indicating where the collision point is. So we can see that we're kind of driving our chamfering tool a little bit too deep as we're moving around here. I can turn on the specific toolpath wireframe for those. Again, I could kind of click around that to line my code up, or I can click directly on the collision object to see where in the program I was at that particular point. So you could certainly go into your CAM system again and change the depth of the chamfer tool on that and repost. And if you do that, you don't have to import or create this whole process again. All you have to do is right click and remove your old G-code and just replace it with a new one. And it's going to apply your new posted code to the setup you already have. And then you can simulate again and make sure that you don't have these type of collisions. The other option is if these type of areas, or you maybe were in soft jaws in your project's case and you wanted to define these particular jaws as machinable, so it didn't cause a collision, you're okay with running it a little bit deep throughout there. Obviously, probably not that much. But in the case of that, you can go directly into the setup and you can pick the vices in question. And I can go to the property and change it from fixed or movable to machinable. And that way, if it touches this, it's not going to cause a collision inside NC Civil. Now that I've changed that, I'm going to run it through one last time. This time I'm going to use break option and end result, as you see here. That way I can just hit play, and it's going to fire ahead as fast as possible in the program until it sees an error. If we had one, it should be clean at this point, and then it would stop automatically. But the idea is it's not going to see, you're not going to see personally any changes inside the stock until it gets to the flip part, and then it would stop automatically if there was an issue. And if you remember, if we go back to the process info, this program was a little bit over 13 minutes in programming time, and we're doing that simulation in almost like around 13 seconds. There's our final result. And if I jump back to our process errors, yes, this window should be blank now, and we're green, so that means we had no more collisions. You can actually put the material back on the part if you wanted to see that. But the other thing you'll notice in the window is we have these couple of hanging pieces that would fall off in the real machine. And we have a couple ways that we can deal with those before we move to the final step. One of them would be to just right-click directly on one of the pieces, and you'll have the option to delete this as scraps. So anytime NC Simul detects a breakage between two of the part models, you're going to see this option to do so. So I could remove that one specifically. Or if we had a bunch of these, you could also click on the main part and say keep as machine part, and it's going to delete everything that is not in contact with that. That's one way of doing it manually if you kind of wanted to control specifically which ones you were getting rid of. But if you wanted to automate it, that's an option as well. So we could have added this function called scraps management, and you just tell it the machining type and the criteria to keep for milling. So I could say keep the largest volume in any case, and any time that the stock was split like that, it would automatically delete the smaller volume. That way there wouldn't be any collisions intermediately if a tool had come in and touched one of those while the process was still running. So that's basically it for step 2. We're clean down here again, so we're good for both 1 and 2. And then all that's left is to verify that we've cut a good piece. And to do that, I'll first move up to the Measurements tab. And this allows us to take a measurement off any 3D object in the environment. So you could take it off the machine table, the fixturing, the part specifically, the stock specifically. But any of these tools will work. So maybe, for instance, I wanted to see what my final radius was on the corner of here. I can come in here, take a couple measurements off the inside of this curve, and it'll show me the curvature of that both in the 3D window and down here in the measurement window. And I can right-click and print or export any of these measurements if you want to kind of create a setup sheet with that, and of course we can output those into the documentation if you did go down that route. The other one we were talking about originally was the comparison tool. So if I click on that, we're going to get the difference between the original part model and what we just cut. And I'm just going to flip it to the result in the second operation so we can see what we kind of ended with. And there you go. So again, green is within your specified tolerance. Red are your gouged areas, so maybe the chamfering wasn't modeled in the part model, but we did it in the real program. Same with the engraving. And then if we had any excess material, we would see it in blue like we did before we flipped to the second operation. And these can all be set up manually if you wanted to increase the step value between each of these segmentations, if you want to create the different minimum and maximum for the scale. But you can also kind of drag them manually in here if you wanted to open up the good tolerance to a little bit more and then still have more specific tighter ones as it fell out of that. That's one way of doing that. And then the final thing to show you, which would be a little bit more specific of a comparison, would be the gouge material, for instance. Surplus is the same thing, but the opposite. This runs a black box simulation of the same simulation that we just saw, and then outputs a table more specifically of the volume that has been gouged. And you can set the limits on this volume so that they're not coming out as small as that we're going to see right now. You can also sort the volume by biggest or smallest gouge, and it'll show you exactly which tool and where those were occurring at. But that's basically it. If you were happy with how the project looked at that point, you'd be good for all 3 steps of the NC-SIML process. The verification, nothing's going to alarm out the machine when you send it out there. The simulation, nothing's going to crash when you're running it. And the verification, we're going to create a good piece at the end of the day. And all you have to do at that point, you just kind of look over here. And if you've modified anything inside NC-SIML, like I did with that Z value, it'll have a little modified symbol next to the original program name. And I just come over here to this floppy disk icon, say Save Program, and then I can output that program to wherever your machines read from, for instance, on the network or wherever you save your final G-codes. And I can save that as a different rev than what got posted originally. Then you're good to go. So yeah, at that point, I think we can open it up to the question and answer session. If you guys have been able to kind of sort what's been coming in as we've gone along, I'd be happy to answer as much as I can. And if I don't get to yours, or if there's something I can't answer for whatever reason, we can directly get back to you in an email with that. But go ahead.